Okay, here's part two. So here's a picture, a diagram of the scenario we're talking about. We got this Platonic idea of rotational motion here, and we're using light to make a shadow of that motion, project that motion onto one dimension. And we're going to use that rotational motion to sort of represent and talk about the motion in the x direction in this case. Okay, so here's the scenario. We've got a ball or some kind of object engaging in circular motion with a radius, in this diagram, a radius a, and the shadow, if the light is coming from above, is on the x-axis, and we know the function, or a function, for the x-coordinate of that point. It's the hypotenuse times the cosine of the angle. Okay, and I've got that redrawn here, so I'll stop sharing the screen for a second. And here we are. So we've got our circle of radius r. We're rotating counterclockwise with angular velocity omega. Suppose we started from some initial position theta 0. After some amount of time, our angle is going to change by that amount. The total angle relative to the x-axis as a function of time is where we started plus how much we changed. In other words, that, which isn't really a surprise. That's the rotational kinematic formula that we developed back in chapter 9. Or I'm sorry, chapter 8. And you might have realized by now that we're talking about chapter 11 here. We skipped chapter 10. We'll come back to it. Chapter 11, I think, is the next thing naturally to talk about. We'll cover half of it today. We'll cover the other half next week. And we'll go from there. The other thing I wanted to mention before we go any farther, thinking about nuts and bolts, the lab for this week is our next lab that's going to require a full lab report. And I know we're still waiting for feedback on the first lab report. I'll be posting those comments to Canvas when I post the grades, so you can see those comments when you log in, so you'll know what the story is and how to, ways you can improve for the next one. Any questions about that, just let me know. Sorry to kind of mix the nuts and bolts in there with the lecture. I just wanted to make sure I didn't forget to say that. Okay. The x-coordinate in that picture that I just showed you, the x-coordinate that we, of that point along the x-axis, if that's where the screen is, right, and we're shining light down from above my whiteboard here, the x-coordinate of the point where the shadow is, we know is the hypotenuse and the hypotenuse r cosine of the angle. And the angle as a function of time, we know, is this expression, theta 0 plus omega delta t. This is, and I said delta t, that's t final minus t initial, but let's start the clock at 0. So when we're saying delta t, let's just say t. T minus 0, just t. So then this becomes a function for x of t. So you tell me what time it is, I can tell you what the x coordinate is of the shadow moving back and forth along the x-axis. Now, in order for this trick to work, this like Platonic idea of circular motion as a model for horizontal motion in one dimension, periodic oscillation. In order for this trick to work, we have to make sure that the circular motion that we're imagining actually matches the motion that we're seeing in front of us. So we've got an object moving back and forth between some maximum point of distance away from an origin and through the origin to some, maximum negative distance away and then back. The maximum distance from equilibrium that's when the rotating object in our imagination lives on the x-axis. That's the farthest away we can possibly get in the x direction from the center is when we're on the x-axis, and that distance is the radius of the circle we're imagining. So the radius of this circle, that is our Platonic idea for how to represent oscillation. That'll work as long as the radius of that circle is the maximum distance from equilibrium. Maximum distance from equilibrium, and this is a trigonometric function. Okay, I gotta stop for a sec and talk about trigonometric functions, because we're sitting here looking at a general trigonometric function, so I want to make sure that we're square on how that behaves. Give me a second. Okay, so this is the picture we last looked at. There's one more I want to show you. Anytime you think about a trigonometric function, think about an old cathode ray computer monitor. Well, anyway, Google it. So, old school computer monitors used to have these 4 buttons on the bottom to change the picture. We could change the horizontal position of the picture. We could change the horizontal size. We could change the vertical position, and we can change the vertical size. Every trigonometric function that we want to graph has the same 4 dials on the front, the same 4 buttons, just like an old school cathode ray computer monitor. Okay, so think back to pre-calculus when we first talked about graphing trig functions. Let's take another look. Our prototypical cosine function, oops, I'm sorry, that's a sine function. Our prototypical cosine function looks like that. And there's some, let's see, we've got the distance here, the maximum distance from equilibrium. We called that y is a function of x equals a cosine bx plus c plus d. And that distance from equilibrium, that was our parameter a. A for amplitude, right? That's the button on the monitor that handles the vertical size. Vertical size of the picture. The bigger A is, the bigger the picture, the more space it takes up. Parameter D handles the vertical position. Our sine and cosine functions are symmetric about that center line. If we change parameter d, then we move the center line up or down the page. So it puts the center line at the line y equals d, and then we oscillate above or below that. Parameter b, this came up when we were trying to graph trig functions by hand from the function. Handles the horizontal size, the horizontal space that we need in order to make one full cycle. And if you remember sine and cosine and their inverse functions, whoops, typo there. The period of a trigonometric function like that is 2 pi divided by parameter b. So the bigger b gets, the narrower the picture. Every cycle takes less horizontal space. The only thing left is the horizontal position, and parameter c handles that. We defined a thing called phase shift, and we set it equal to negative c over b, is compared to one full rotation by how much are we shifting it relative to one full rotation. So how much are we shifting c compared to one full rotation b, and that's our parameter that tells us how big one full cycle is going to be. When you first learned it, your instructor might have put the minus sign here in like the prototypical form of a trigonometric equation, that like sort of baseline equation there. If the minus sign lives there, when you calculate the phase shift, there doesn't need to be minus sign, it's got to be plus. But if you put this as a plus sign, then you need the minus sign here. Bring this all up because this coefficient of the trig function that we're talking about, that's r. And we just said that r needs to be x max, the maximum distance from equilibrium, which is what amplitude has always been. So in order for our model, our Platonic circle, to work as a model for oscillation, the radius of the circular motion that we imagine has to be equal to the amplitude, the size of the oscillation from equilibrium up and down. That's one piece of the puzzle. The other thing we need to be careful about when we're imagining our Platonic circle is with what angular velocity does this thing actually rotate? If we pick the wrong angular velocity, then our imaginary object is going to go around a circle too often, or too often or too infrequently. So, I mean, we got to make sure that omega here lines up with I guess the lines up with how often the mass at the end of the mass at the end of the spring makes a full cycle. I just don't know exactly what that dependency has to look like. So this is still undecided. We got to figure out what omega that we imagine should be equal to so that the Platonic circular motion that we're imagining is actually a model for oscillation. All right, I gotta erase some stuff. See, and when we say R, I'm going to change that to amplitude or X max. The next piece we do, for simplicity, just to keep things kind of nice and clean written, let's choose the initial time and initial position. Let's start the clock when we are on the x-axis as we're going counterclockwise. So we don't need the initial theta because it's 0. That we start when theta initial is 0. So the only thing we need in the argument of the trig function is omega t. Just keep things kind of nice and straightforward there. Now, remember, this is meant to represent the situation where we've got a spring and a mass. Let's make it horizontal so that we don't need to worry about gravity. And we're going to pull that mass, stretch it, so that the initial position is here. This is the equilibrium position. I'm going to make that the origin of the coordinate system so that we don't have to worry about constants rattling around in there. So we could be past 0, or we could be the other side of 0 with a negative x coordinate. But this is the scenario right at the beginning. We're going to stretch the spring so that our x coordinate is x max, and then we're going to let go. Just before we let go, that's a stretched spring, a spring that's stretched this far. We know how much energy that system has. The potential energy of a stretched spring is 1/2 k x squared, the distance it's stretched from equilibrium, and we know that that's x max. On the way back through, we let go. It's going to spring back. Let's not worry about friction for right now. Let's make sure that this is a conservative situation. If there aren't any non-conservative forces, then the energy we have is the energy we have. And on our way through equilibrium, so that the spring is neither stretched nor compressed, none of the energy can be stored in that spring, so it all has to be kinetic. So the kinetic energy we have on our way through equilibrium has to be equal to the potential energy we had when we started, because none of the energy is potential anymore. All of it has to be kinetic. Half k x max squared, but that's okay, 1/2 mv max squared. The kinetic energy that we're going to have on our way through equilibrium, because that's when we're going the fastest. None of the energy is stored. It's all being expressed as kinetic. But we know that it has to be as much as we started with. Okay. So let's see, V max squared k over m x max squared. Okay, that's fine. We can take square root. The maximum speed we're going to be able to have, k over m x max. I guess plus or minus. We could be going one way or the other way, right? Still not really sure how that lets us talk about omega. But wait a minute. This velocity that we're tracking is the velocity in the x direction. Now, generally speaking, the velocity of the linear velocity of this rotating thing that we're imagining is in some direction that isn't in the x direction. It's tangent to the circle. It has some x and some y component. There isn't any real y component because we're just talking about motion back and forth, really. But our rotating object has a velocity that is in the x and y directions, except for those times when either it's at the very top, traveling only to the left, only in the negative x direction, or it's at the bottom, traveling only in the right, only in the positive x direction. Now, those are both the times, both the cases when our position of that object is at equilibrium, which is this position that we're talking about. So Vmax, in other words, the moment when our velocity is, well, the velocity of this imaginary rotating thing is entirely in the x direction, in the direction that we actually care about. At the instant that's true, we've got a thing rotating with omega in a radius r, and we know the tangential speed should be v. And when that tangent is directed in the x direction, in other words, when its x component is maximum, we know what it should be equal to, but it should also have a magnitude equal to omega r. But r, the radius of that circle that we're imagining, we said has to be x max. So omega x max needs to be equal to, well, I guess, again, we could be going one side or the other. So I'm just going to get rid of that plus or minus. I think that's just confusing me. The magnitude, we'll write it this way, needs to be the positive square root or omega x max. But then, all right, we've got an x max on both sides of that equal sign. And that's the other key. In order to make sure that our Platonic imaginary circle rotating object actually does have a shadow that moves the same way that this mass moves, we need two things to be true. We need the circle we imagine to have a radius equal to the amplitude of the oscillation, and we need the angular velocity of that rotation that we're imagining to correspond this way to the spring constant and the mass that's oscillating. If we can do that, if we imagine that, then this is a good prototype, a good model for horizontal oscillation because it makes conservation of energy possible. The only way that this is equal to that is if the energy is conserved and we make the definition that omega is root k over m. If we don't have omega equal to that, then we can't equal these two sides. Since they got to be equal, we insist that this is true so that energy is conserved. That's how we get a imaginary circular motion to describe, to match, to align with real physical motion. Okay. So, conservation of energy has shown us a way to imagine a platonic rotating object such that the shadow, the projection of that object onto the x-axis, describes the actual reality of the oscillation we're trying to talk about. What else, now that we have that sort of documented, what else can we say about the motion? We've talked about what the maximum speed is, but if I really want a full description, I want to talk about the position, the velocity, and the acceleration as functions of time. Just at any time, I can tell you the position, velocity, and acceleration. Okay. This is still true. The maximum potential energy that we started with when we let go of the mass is 1/2 k x max squared. And if energy conservation is going to be still a thing, let me write down that omega needs to be equal to root k over m, just so I don't lose that. At any point, like we let go at time 0, and then sometime later we're here at some position x. I don't know what it is, but at that position, we're moving a little bit, and the spring is stretched a little bit. So the total energy we've got, potential energy plus kinetic energy, needs to still be equal to the amount of energy we have together, just, that we have to work with. The amount of energy we have to work with is the amount of potential energy we started with. The potential energy we have here, 1/2 k x squared. And the kinetic energy we have here is mv squared, whatever that velocity is, but we could solve for that velocity. Let's multiply through by 2, move this term to the other side. K x max squared minus k x squared. You know what? Let's factor out a k that way, and then we're going to divide by m. And we can take a square root, and now we have velocity. If you tell me where we are, if you tell me the x coordinate, I can tell you k over m x squared max minus x squared. Oh, wow. Look at that. K over m. That's omega. The square root of k over m is omega. That's pretty cool. Okay. Now, I'd like to factor x max squared out of both terms inside the radical here. Now, it's not an immediately intuitive thing to do, but it's going to pay off in a second. So we've got the square root of x max squared, 1 minus x over x squared over x max squared. The square root of x max squared, well, that's just x max. And we got to square root this thing, whatever that is. Omega x max, that's what we wrote a second ago, was the maximum speed. All right, but what is this radical 1 minus x squared? Okay, so let me rewrite this. Let me start again. Let me write it way up here. That the velocity as a function of x coordinate is v max, our maximum speed, because that's this thing, times the square root of 1 minus x squared over x max squared. What is that? Well, first of all, that is a function for the velocity at any position x. Tell me what x is. Oh, we can talk about what the velocity is. It's not quite a function of time, though. And that's the piece that I'm kind of aiming for now. This is the x coordinate, and then this is the y coordinate. And the y coordinate here, according to the Pythagorean theorem, right, r squared equals x squared plus y squared. Okay, does that help any? What else do we know? We know that, what if we divide both sides by r squared? X squared over r squared plus y squared over r squared. Now, x squared over r squared, that's adjacent over hypotenuse squared. So that's cosine. That's cosine squared of the angle. But opposite squared over hypotenuse squared, that's sine. Oh my gosh, wait a minute. X squared over r is x max squared. So if we subtract this one to the other side, that's 1 minus x squared over x max squared equals sine squared. And we're taking the square root of that. So we'll take the square root of this, and we can do that to both sides. So this thing, sine theta. So, wait a minute. So now we're saying v of theta, because you tell me theta, I can tell you the value of this, but theta is omega t. So this is the velocity as a function of time. An amplitude and a trig function, just like the position function. And in fact, those of us who have had derivative calculus will recognize this function as the derivative of this one. that factor of omega that we need for V max, it comes from the chain rule when we take the derivative of cosine. There's a plus or minus thing going on here, those of us who are keeping track. And we know that because sometimes we're going to the left, sometimes we're going to the right. Technically, when we take the derivative of cosine, we're going to get a minus sign, but it's a little bit ambiguous. We got the plus and the minus. So we need that minus sign there to really get things to work out. When the argument of sine is between 0 and pi, we're traveling to the left because we're going around this way, so we're always going back to the left. Sine, in that case, though, is positive, so that minus sign tells us we're headed to the left. As soon as we come back around, now the angle is bigger than pi, so sine is negative because we're in the bottom hemisphere of the xy plane. So that negative sign cancels this negative sign, and it means we're coming back to the right. Okay. So we've got a function of time for position. We got a function of time for velocity. We just need a function of time for acceleration. In this case, there's no gravity in Newton's second law. So if we write Newton's second law, the only force acting is the restoring force from the spring itself. At whatever point x we are, if we're to the right of 0, x is positive, and the spring's going to try to pull us back. If we're on the other side, x is negative, and the minus sign is going to cancel that, push us to the right. Equals ma. So a equals negative k over m x. K over m, there it is again. Negative omega squared x. So we've got an acceleration as a function of x. We know, let's see, we'll write that, a of x. If we choose the largest possible x, we can find the maximum acceleration using x max. And if we want a function of time, we already know x as a function of time, so we can just throw that right in here. Acceleration as a function of time gets us negative omega squared x max times cosine omega t. That result is a big deal. We arrived at this result from Newton's second law, and it's Newton's second law for an oscillatory thing. As we're pushed to the right, as we displace the mass to the right, the spring tries to pull us back. The farther we go, the stronger that force is. As we push the mass to the left, the spring tries to push us back. And the farther to the left we go, the stronger that force is. This is an expression of a restoring force, one that tries to push us back to an equilibrium that is proportional to, so it's a restoring force, that minus sign is proportional to the displacement. Anytime we can say that the acceleration is proportional to our displacement from equilibrium, and that the system is trying to push us back the other way towards equilibrium. This is our sort of clue that we're talking about oscillation, harmonic motion, simple back and forth periodic motion. anytime, any new situation, any new scenario, any new, equipment, if we can get the acceleration to look like it's proportional to the negative displacement from equilibrium, then we're talking about an oscillatory system. We're talking about simple harmonic motion. Okay. There's one more thing we got to say. That'll be in the next video for this week. And then there's one more video that I want to post that goes with our activity for the lab this week, in addition to Sean's introductory video. Yeah, one more short video of lecture content this week, and then we're good to go.